Hi guys. Since we have two homework due this week, and I only have one office hour, so that's why I'm recording a separate video to discuss and possibly give you some hints about home assignment 4. So this is how it works. Maybe so because the Zoom on Brightspace doesn't allow me to automatically record the session, so I'm screen recording every office hours and then I will post those recordings to my YouTube channel. Um, I will send you guys a link maybe every time after office hours, but actually you only need to have one link. And by clicking that link, you can go to my particular one video in my YouTube channel, and then by clicking my name, you can go to my profile. Um, I don't know if you can see this. I'm sharing my screen, but um, when you when you come into my profile, you can see all of the related videos. Some of them I posted last semester, and this semester I only posted one, which is on the very top. Some discussion about home assignment 3. Today I'm gonna discuss home assignment 4, and again I will post the video and I will send you the link. Right, so this is home assignment 4. So this chapter covers basically Poisson distribution. Home assignment 3 covers hypergeometric distribution, and you can review those concepts through the 4.3 and 4.4 chapters in textbook. Specifically for home assignment 4, it's about it's about Poisson distribution and exponential distribution. The last question is about exponential distribution. So first, let's look at the first two questions, the flying bomb. To answer this question first, you have to like discover, oh, I'm doing a Poisson distribution. Poisson distribution and binomial distribution are very closely related. Um, but one key difference is for a binomial distribution, the probability is not very high. Like when I toss a coin, I'm sorry, the probability is reasonably high because when you toss a coin, you have one half probability of giving a head or giving a tail, and one half is arguably high. Um, that's how basically a feature of binomial distribution. But for Poisson distribution, there's two key features. First, the number of observations has to be big enough. N has to be very big. In this case, the number of observations is 576, which is arguably big. And then another feature is the probability should be very small. Um, in this case, the possibility of oh no, like the possibility here, 576 is not the sample size, but again, it's probability, right? The possibility of a bomb landing in one sector is only 1 over 576. The number of observations is here. You just add all of those up. Um, you should do like 229 plus 211 times 1 plus 93 times 2 all the way 7 times 4 and 1 times 5. You just assume like 5 plus is just 1 is just 5 sectors, right? So basically here by adding all those observations, you get like 535 observations, I guess. And the probability is very high, is very low. Like bombing each section, the probability is just 1 over 576. So here, like satisfy two features of Poisson distribution. And lambda is just n times p, and you get the lambda, which should be very low, arguably low, because you use a very big number times a very small number. Use a very big sample size times a very small probability, and that number should not exist, 10, I would say. Otherwise, the Poisson distribution is not a very good estimation of binomial. So basically, you just need to use the formula of like the probability density function of the Poisson distribution. I guess for zero hit, I guess it's just lambda to the power of 0 divided by 0 factorial times e to the power of negative lambda, and just plug in lambda equals n times p, which is very small, and you get the probability of like a location receiving 0 bomb, a location not being bombed, and you use that probability times the number of observations, and you get the theoretical frequency, and then you compare that theoretical frequency with the actual frequency, 229, and to see if there's a huge difference. Like if there's no huge difference, it means probably actually the bomb is landing at random. But if there is a huge difference between your theoretical number and our actual observation, then it means the bombs are not landing at random. Question number 2, pretty similar. Again, you have a very high observation, you have a very high sample size, 400. The probability is just 0.01, pretty low. Again, you use Poisson distribution. Lambda is n times p. 400 times 0.01, which equals 4, is reasonably small, but maybe in this case, it's not the best way to approximate the binomial distribution, but we can still do that because lambda equals np equals 4 is not big, and we can still use Poisson to estimate binomial distribution. Again, the key to this question is you find the probability of 400 people showing up, of 399 people showing up, 398 people showing up, etc. You just have to think about it conversely, right? What does it mean? Like 400 people showing up means everyone showing up, right? Nobody is not showing up. So you just use the probability density function of p0. Again, is like lambda to the power of 0 divided by 0 factorial times e to the negative lambda. And just by doing, I guess, all the question A, B, C, you just have to play around the words, right? But most important is you find P0, P1, P2, P3, which is what's the probability of 3 people not showing up, what's the probability of 2 people not showing up, and you use Poisson distribution to do it. The third problem is it's an exponential distribution. It's relatively easy, I would say, right? You have learned the probability density function of exponential distribution. It's just p equals e to the power of negative lambda t, right? So basically the two atoms have exactly the same probability density function, which is e to the negative lambda t. And notice that what is the probability of both both of them survive within the time t, right? Think about it, because those two atoms are independent, right? So both of them surviving, the probability of both of them surviving time t is just the first of them surviving time t times the second of them surviving time t. And if you use the probability density function, it's just e to the minus lambda t times e to the minus lambda t. And you get the probability density function for the new event, which is the two atoms surviving time t. And by observation, it's again exponential distribution. So basically that's it. Hope those kind of videos will be helpful. Um, and as always, I will hold another office hours in Thursday night. You can directly join the office hour by going to Brightspace and clicking the Zoom, and you can see like week 5 Victor's office hours, and just clicking